Here is a question that ought to keep you up at night. When light leaves a star that is 1 billion light years away, it travels for 1 billion years to reach your eye. 1 billion years. That is longer than complex life has existed on Earth. And yet, here's the funny thing. From the light's own point of view, if we can even say such a thing, no time has passed at all. Not 1 second. Not 1/1000th of a second. Nothing. Zero. The journey that takes 1 billion years for us takes no time whatsoever for the light itself. How can that be? How can something travel for 1 billion years and yet experience no time? By the end of this lecture, you will understand exactly why this happens. And I do not mean you will just nod along. I mean you will really get it in your bones. You will see that this is not some mystical poetry about light. It is a direct, unavoidable consequence of how space and time actually work. And once you see it, you cannot unsee it. Now let us start with something simple. Let us start with time itself. What is time? You might say it is what clocks measure. Fair enough. But what do clocks really do? A clock is just some regular process that repeats. A pendulum swings back and forth. A quartz crystal vibrates. A cesium atom oscillates between two energy states. We count the repetitions and call that time. So time for any given object is really about the processes happening inside that object. If you have a little clock in your pocket, time for you is defined by what that clock does. And if the clock stops, well, time stops for you, at least in any meaningful sense. Now, here is a strange fact. Suppose you and I each have identical clocks, beautiful, precise clocks. We stand next to each other, and our clocks tick together. 1 second for you, 1 second for me. Perfect agreement. But now, suppose you get on a rocket ship and fly away from me very fast. What happens to your clock? You might say, well, nothing happens to my clock. It is the same clock it always was. It ticks at the same rate it always did. And from your point of view, that is absolutely true. Your clock keeps perfect time. You feel nothing strange. 1 second follows another, just as it always has. But here's the strange part. From my point of view, watching you zoom away, your clock is running slow. Not because it is broken, not because there is anything wrong with it, but because of the nature of space and time themselves. Your clock actually ticks slower relative to mine. And here's the thing, this is not an illusion. This is not some trick of perspective. This is real. If you fly away very fast and then come back, we can compare clocks. And yours will have ticked fewer times than mine. Less time will have passed for you. This has been tested many times with atomic clocks on airplanes. It is a fact about nature. So time is not absolute. Time depends on how you are moving. The faster you move relative to me, the slower your time runs relative to mine. This is called time dilation. Now you might ask, why? Why should motion affect time? What is the connection between moving through space and the rate at which time passes? This is where Einstein comes in, and it starts with a very simple observation about light. You see, light is strange. It does not behave like other things. If I throw a ball at 10 miles an hour while I am standing still, and then I get on a train moving at 50 mph and throw the same ball, the ball goes faster relative to the ground. That makes sense. Speeds add up. But light does not work that way. If I shine a flashlight while standing, still the light goes at the speed of light. We call that c. About 186,000 ms or 300,000 kilometers s. Very fast. Now if I get on a rocket ship going half the speed of light and shine the same flashlight forward, you might expect the light to go at 1.5 times c. After all, my speed plus the light's speed. But it does not. The light still goes exactly at c. Not faster, not slower, exactly c. This was discovered experimentally, and it was very confusing. How can that be? How can light always go at the same speed? No matter how fast the source is moving. Einstein realized that the only way this can make sense is if space and time themselves are different from what we thought. If the speed of light is truly constant for all observers, then something else has to give. And what gives is our notion of absolute time. You see, we naturally think of time as a river flowing at the same rate everywhere. 1 second is 1 second everywhere for everyone. But that cannot be true if light always goes at c. The mathematics forces you to conclude that time flows at different rates for different observers. And the key factor is velocity. The faster you move, the slower your time runs relative to someone at rest. Let me give you an analogy to make this more vivid. Imagine you are walking across a field. You can walk north, or you can walk east, or you can walk in some direction in between. The total distance you cover depends on how you divide your motion between north and east. Now here's the key. Suppose you have a fixed walking speed. Say you walk at exactly 1 mile per hour. If you walk purely north, you cover 1 mile north in an hour. If you walk purely east, you cover 1 mile east in an hour. But if you walk northeast, you cover less than 1 mile north and less than 1 mile east, because your motion is divided between the two directions. Space and time work in a similar way. Everything in the universe is moving through space-time, and everything moves through space-time at the same total rate. We might call this the cosmic speed limit. And here's the beautiful thing. That cosmic speed limit is exactly the speed of light. If you are sitting still in space, not moving at all relative to me, then all of your motion through space-time is directed through time. You move through time at the maximum rate, 1 second per second, as it were. But if you start moving through space, some of your motion through space-time gets redirected from time into space. And that means you move through time a little slower. Your clock ticks a little slower. Time passes more slowly for you. The faster you move through space, the more of your space-time motion is going into space and the less is going into time. Your clock slows down more and more. And here is the punchline. What happens when you move through space at the speed of light? Then all of your motion through space-time is going into space. There is nothing left over for time. Your clock stops completely. Time does not pass for you at all. This is why time stops for light. Light moves through space at the maximum possible speed. It uses up all of its motion through space-time. Just traveling through space, there is nothing left for moving through time. Let me say that again because it is so important. Everything moves through space-time at the same total rate, the speed of light. If you use all that motion for traveling through space, you have none left for traveling through time. That is what light does. That is why time stops for light. Now let me give you another analogy to make this concrete. Suppose you are on a highway and there is a speed limit of 100 miles an hour. You can drive north at 100 mph or east at 100 mph or at some angle in between. If you drive purely north at 100, you make no eastward progress. If you drive purely east at 100, you make no northward progress. But if you drive northeast at 100, you make some progress in both directions, but less than 100 in each. Space and time are like north and east on this highway. Your speed through space-time is fixed at c, the speed of light. If you use all that speed traveling through space, you have no speed left for traveling through time. Time stops. Now, here is something I should be very careful about. When I say time stops for light, what do I really mean? Does light experience anything? Does a photon have a point of view? This is where we have to be honest about what we know and what we do not know. Photons are not little people. They do not have experiences in the way we do. So when I say time stops for light, I mean something very specific and physical. I mean that if you calculate what a clock would read if it could somehow travel at the speed of light, the answer is that it would not tick at all. No time would pass on that clock. We cannot actually build a clock that travels at light speed because clocks are made of matter, and matter cannot reach the speed of light. Only massless things like photons can travel at c. But we can take the limit. We can ask what happens as you go faster and faster, closer and closer to the speed of light. And the answer is that time slows down more and more, and in the limit time stops. So when a photon is emitted from a distant star and travels for 1 billion years to reach your eye from the photon's point of view, there is no journey. The emission and the absorption happen at the same instant. The whole trip takes 0 time. This is one of those ideas that sounds like poetry, but is actually hard physics. It falls directly out of the equations of special relativity. There is no way around it. Now, let me check myself. Let me make sure I can explain this to a bright 12-year-old. All right, young friend, here is the deal. Everything in the universe is always moving through space and time together. Think of it like having a limited budget. You have a fixed amount of motion to spend, and you can spend it on moving through space or moving through time, but not both fully at once. If you sit still, not moving through space at all, then all your motion goes into time. Time passes at the normal rate. But if you start moving through space, you are using some of your motion budget on space. So you have less left for time. Time passes slower for you. Light moves through space as fast as anything can possibly move. It uses up all of its motion budget on space. There is nothing left for time. So time does not pass for light at all. Does that make sense? Good. Now let me address a common misconception. People sometimes think that time dilation is just about how things appear. They think, oh, it just looks like the clock is running slow. But really, it is running at the normal rate. This is wrong. Time dilation is not an optical illusion. It is not about appearances. It is a real physical effect. If two twins separate and one travels at high speed while the other stays home, when they reunite, the traveling twin will be younger, actually physically younger. Fewer heartbeats, fewer thoughts, fewer birthdays. This is real. The confusion comes because we are used to thinking of time as absolute. We think there is some universal clock ticking away in the background, and everyone's local clock is just keeping track of that universal time. But there is no universal clock. There is no background time. Time is local. Every object has its own time, determined by its own history of motion. This is hard to accept because it is so different from everyday experience. But everyday experience is limited to low speeds. We never move at speeds where time dilation is noticeable. If you fly in an airplane, time dilation is real, but it is tiny billionths of a second. You cannot feel it, but it is there. At speeds close to light, time dilation becomes huge. At 90% of light speed, time runs at about half the rate. At 99%, time runs at about 17th the rate. At 99.9%, about 122nd, and so on. As you approach light speed, time slows to a crawl and then stops entirely. Another misconception is that there is something special about light itself that makes time stop. People think light has some magic property that freezes time, but that is not quite right either. What is special is the speed. The speed of light is the cosmic speed limit. It is the maximum speed at which anything can travel through space, and it is the total speed at which everything travels through space-time. Light travels at this speed through space because light has no mass. Anything without mass must travel at exactly this speed. It cannot go slower. If there were other massless particles, they would also travel at c, and time would also stop for them. In fact, there probably are other massless particles. Gluons, which hold quarks together, are massless. They also travel at c. Time stops for them too, and gravitational waves, ripples in space-time itself also travel at c. In some sense, time stops for them as well. So it is not about light specifically, it is about the speed. The speed of light is special because it is the structure of space-time itself. It is built into the fabric of the universe. Now let me take you through a thought experiment. This is the kind of thing I love to do. Let us really see how time dilation works. Imagine I have a very simple clock. It is called a light clock. Here is how it works. I have two mirrors, one above the other, separated by some distance. Let us say 1 meter. A pulse of light bounces up and down between the mirrors. Each time it completes a round trip up and back, the clock ticks once. Now this clock is sitting still in my laboratory. The light goes straight up, hits the top mirror, comes straight down, hits the bottom mirror, tick. The time for one tick is just the round trip distance divided by the speed of light. 2 meters divided by c. Very fast ticks, but that is fine. It is a clock. Now suppose you put this clock on a rocket ship that zooms past me at half the speed of light. What do I see from my point of view? The clock is moving horizontally. The light pulse goes up. But while it is going up, the clock is moving to the side. So the light does not go straight up. It goes diagonally up and to the side. Then it comes back down also diagonally. Here's the key. The light still travels at c. The speed of light is the same for everyone. So the light is traveling diagonally at c, but the diagonal path is longer than the straight up and down path. So it takes longer for the light to complete the round trip. You see what happened from my point of view? Watching your moving clock, the clock ticks slower. The same pulse of light takes longer to complete its journey because it has a longer path to travel, and this is not some trick of the light clock. Any clock would slow down in the same way because all physical processes depend on the structure of space-time, and that structure says that moving clocks run slow. Now you might ask, what about from your point of view on the rocket? From your point of view, you are sitting still and I am the one moving. So do you see my clock running slow? Yes. This is the weird part. From your point of view, you are at rest and your clock is ticking normally. But you see my clock, which is moving relative to you, running slow. Each observer sees the other's clock running slow. It seems like a contradiction, but it is not. The resolution comes when you try to compare clocks directly, and that involves acceleration, which gets complicated. But the key point is this: if you keep moving at constant speed forever, you and I will each see the other's clock running slow, and there is no paradox. The paradox only seems to arise if we try to bring the clocks together to compare directly, and when we do that, one of us has to accelerate, and that breaks the symmetry. Let me take this further. Suppose you are on a spaceship traveling at 99% of the speed of light. What is time like for you? From your point of view, everything is normal. You get up, eat breakfast, do your work, go to sleep. 8 hours of sleep feels like 8 hours of sleep. Nothing strange. Your clock ticks at the normal rate, 1 second per second. But from my point of view, watching you from Earth, your clock is running very slow. For every second on your clock, about 7 seconds pass on mine. You seem to be living in slow motion, not because of any trick, but because time itself is passing more slowly for you. Now suppose you travel for what seems like 1 year to you. You age 1 year, you have about 365 days of experience. But when you check how much time has passed on Earth, you find that 7 years have gone by. Your friends have aged 7 years while you aged 1. This is real. This is not science fiction. It is a direct consequence of the equations of special relativity, and it has been tested many times. At even higher speeds, the effect is even more dramatic. At 99.9% of light speed, time slows by a factor of about 22. Travel for 1 year of your time and 22 years pass on Earth. At 99.99%, about 70 years pass on Earth for every year of your time. And as you approach the speed of light itself, this factor goes to infinity. At exactly light speed, infinite time passes on Earth for 0 time on your clock. Time stops for you completely.